All right, today we're going to take a look at section 2.2. We're going to be taking a look at diagrams that are called Venn diagrams and subsets. These are diagrams you may have seen before. They are often taught in elementary school. It's where you first see them. My daughter came home with them, one of my daughters, one of the older ones, when she was in second grade. They didn't use them for quite the same thing that we're going to take a look at them, but they were using Venn diagrams. So they are something that you may have seen before. So let me first sort of draw a picture of a basic Venn diagram. So a basic Venn diagram has a rectangle, and it has one or more circles inside of the rectangle. So I'm going to draw it right now with just one. It could have more than one. It could have two or three. None of the diagrams that you have will have more than that. The circles could overlap. They could be disconnected. Within this Venn diagram, this rectangle is called U, and this U is the universal set. Now, you remember we talked about sets last time. Sets are just collections of things. So this rectangle could be the people who live in Dr. Hand's household. This rectangle could be the students who are in this class, like enrolled in this class. Okay, so it could be any of those kinds of things. And then this circle inside is some other, typically smaller collection of things that are already in this category. So if we were to do this is a set. We could talk about, again, the rectangle being all the people who live in Dr. Hand's household, and then the circle being the girls. Okay, it's just a smaller grouping of the bigger category. All right. So a complement of a set is described as the following, and we'll go back to our picture so you can see what it looks like from a visual perspective in a moment. For any set A within the universal set, the complement of A, and our book writes it with this prime notation, so it says A prime, is all elements in the universal set that are not in A. And then what you see here is you see that set notation, set builder notation, that we saw last time. This is all elements X, where X is in the universal set U, and X is not in A. Okay, so if you'll flip back to the other page, right, the earlier description that we had over here, I'm going to do a little bit of shading. This set A is going to be drawn in this yellow kind of color. And if we're talking about A complement, I'm going to color it differently. Let's color it in orange. So the orange part that I'm about to color is A complement, and it's everything that's outside of the circle, but still inside of our rectangle. Okay, so U is the yellow and the orange, but the orange is just the complement. Okay, so the verbal description that I had given was Dr. Hand's household is the universal set. The circle A was the girls, so the outside of that would be the boys. Okay, that's how that would be described with that example. All right, so we're going to do another example, a couple of them. So they give us a universal set, and instead of it being people, in my example, it's just numbers, and it's the numbers 1 through 10. Now, if it helps you to draw a picture and put these items in a picture, you can certainly do that. You don't have to, though. So if you're taking a look at this, let's call this set A so that we have a way to refer to it conveniently. They give us a set 1, 2, 3, 4, 7, 10. and this is some set A. And we're trying to find the complement. So we want to find all of the numbers that are in the universal set, which was 1 through 10, that are not in the set A. So what is the first one that you see that's missing? 5. What else is missing? 6. Any others? 8 and 9. So this is the complement. Now 2 looks a little funny because 2 says we want to find the complement of the universal set itself. So imagine what that's asking you. I want to find all the items that are in the universal set, because that's where I started with, right, that are not in the universal set. Well, there's nothing missing, right? So what is it? Empty. It's the empty set. So if I want to find the complement of the entire universal set, it is the empty set. And what do you suppose the complement of the empty set would be?
The whole set.
The whole set U. Okay? So these go back and forth. It's almost like a play on words for the ones that include everything or include nothing. Okay? So the universal set goes to the empty set. The empty set's complement is the universal set. Is that okay? All right. Now, we had talked last time about set equality, and we're going to talk about it again today. We need one more definition before we do, and that's the definition that's the other description of our title of our section, which is about subsets. So subsets of a set. Set A is a subset of B if every element of A is also an element of B. And the notation is that it's written with this sort of squished C, is sort of what it looks like, right here, and a line underneath it. So A is contained in, or it's a subset of B. Now, picture-wise, in terms of Venn diagrams, it looks something like this. So we have these embedded circles. The universal set is still out here, right? And the way the picture works is that this says that A is inside of B. So A is the centermost circle, the way that I've drawn it, and B is this outer circle. Now, if you think of the definition in its verbal form, and it says everything in A is in B, that picture should make sense. The entire circle A is inside of the circle B. Okay? And all of it's inside of the universal set. Now, because of the definition, it's actually possible that A and B are exactly the same thing. They could actually be the same. Because if they are the same, then clearly everything that's in one's in the other. So it doesn't preclude that possibility, and that's actually why you're seeing that equal on the bottom, right? This piece right here at the bottom that looks like an equal sign, like if you had less than or equal to, that's why that equal is there, is because it does have the possibility that they could be exactly the same. Now, if in fact one of them is equal to the other one, like this, A and B are actually equal, then what it means is that A is a subset of B and B is a subset of A. I mean, okay, everything in A is in B, and everything in B is in A. And this is actually another definition of what set equality is. It means you're looking to see that everything in one group is in the other group and vice versa. Right? So we'll do one more definition, then I'll give you a verbal example of where this succeeds and then where this sort of fails. So proper subsets. So if you have a proper subset of a set, it actually means it's a subset, but it's not equal. Like it is not exactly the same. There is something else inside of the bigger set that's not in the smaller one. And what you see notationally is that the equals on the bottom is missing, right? So it's the equivalent from an algebra standpoint of having x is less than 5 and x is less than or equal to 5. Right? They're very similar, very, very similar statements, but one of them actually has the possibility of having equality and the other one does not. So I like to give this example. I have my husband's brother. My husband's brother was married before he's married to his wife now, and he has a daughter from that marriage. So he has 4 biological children. Okay, so his oldest one was from his first marriage, and then he and his wife now. So my sister-in-law, they have 3 children together. Can everybody picture this? Maybe some of your families are like this. Okay, so if my sister-in-law were describing her biological children, that would be a smaller group of people than my brother-in-law describing his biological children, right? So these would be a proper subset notation, right? It's proper, but it's actually not equal. So this notation, where it doesn't have the equals underneath it, could be used. Now, it's important to recognize that it's still correct to write it like this. Okay? Just because something says less than or equal to doesn't mean it has to be equal to, right? But this over here on the right-hand side, A is a subset of B without the equals, is actually a more fair description because it really is a smaller grouping. Now, if I were to describe my biological children, and my husband were to describe his biological children, if you remember the picture, we have one. It's Abby. And so our description would actually make equality statements. They would be equal to one another, right? So some sets will have this idea of being less than or equal to, or a subset or equal to, and some just don't. So what we're going to do is we're going to take a few subsets, or few sets, and we're going to decide which of these symbols, proper subset, both of them, or neither of them, should go in the blank. Now, the general way that I always start with these is I simply ask myself, is everything in the first thing in the second? Is everything on the left also on the right? Because that eliminates some of the options right off the bat. So let's take a look at the first one from that perspective. We've got B, C, and D. Is everything in the set on the left an element of the set on the right? Yes, it is. Okay, it's there. So everything on the left is on the right. What that means is that the word neither doesn't go in the blank. Okay, so neither happens when we've got something on the left that's not on the right. We don't have that, so we've eliminated the word neither. The second thing to ask ourselves then is, okay, so that tells us for sure that we could use this one right here, because that's what that subset means. This is definitely a viable option. The question is simply whether this one also works. You with me? That's our question mark right now. So we know we have the first one, the subset notation. The second question to ask yourself then is it smaller? It's what's on the left does what's on the left have fewer items than what's on the right? Yep. And it does, which means this option works too. And since the option number 1 works and option number 2 works, what's the answer? It's both. So this right here should have the word both in it. And the way this typically shows up in my math lab is kind of a drop-down menu, kind of like a multiple choice thing, where you pick the options, and you're not writing it in, obviously, but you're just picking one of those options, and it would have these 4 options for you to pick from, kind of like multiple choice. Cool? Okay. How about the next one? So, is everything on the left also on the right? Yes, it is. Okay. So going back up to our options, what we've said is that this one works for sure. Okay. Are there more items in what's on the right than there are in what's on the left? No. Right? So if there are the same number of items, which there are here, technically you could put what between them? You could put equals, right? It would be correct, but that's not one of my 4 choices, right? So since it's not one of my 4 choices, so we know this one's no good, we know this one's no good, what we're left with is we're left with the one I've drawn the arrow to already, because there aren't both options available. The only one that fits here of the choices I'm given is this. But equals would be a correct choice if it were an option too, right? It would. Okay, let's try one more time. We have the last example. Is everything on the left also on the right? No. What's the problem?
We have a -1 on the left.
Yep, this one right here, the -1, is the problem, isn't it? Now, it doesn't really matter what the problem is. There's something on the left that's not on the right. What that means is what goes in the blank? Neither. Neither of those are a true statement. In fact, it's sort of interesting to notice that it doesn't work the other way either, right? So all of these items are not over here either, are they? So even if we flipped this one around, it would actually still be neither. That doesn't always happen that way, but this one would be. So, all right, so the number of subsets, how many are there? Well, if we had a small group, and I'll do a real quick example for you if we did. So let's just say we had 3 elements, A, B, C. And we wanted to count how many subsets there are. Okay, so one subset of this is the whole set itself. It's not a very exciting subset, but it is one because everything in it is in the original values. Okay, you got 3 items. But maybe you don't have all of them. Maybe you only have 2 of them. Well, I could have A and B. I could have A and C. Or I could have B and C. Those are all the groupings of 2, right? But maybe I don't have 2 items in my subset. Maybe I only have 1. Okay, so I could have A, and I could have B, and I could have C. There's one subset that's missing. Any idea what it might be? The empty set. Very good. The empty set, again, this is one of those like play on word kind of feeling ones, right? Everything in the empty set is also in the original set. Okay, fine, but there's nothing in it. But that's okay. It still meets the definition. Everything in the empty set is also in the set. Okay, so how many did we get? How many of different subsets did I get down here? There's 8. There are 8 here. How many elements, let's actually write it in. The number of elements, oh, I need this to have a name. Let's call it G. How many elements are in set G? 3. All right, so what's the relationship between 3 and 8? Because it's not super obvious. Like, is it like 3 plus 5? Is it like I've multiplied something? Like, what happened? Well, the way that we get the number of subsets is it's actually 2 raised to the power n. Okay, we have, and n's our number of elements. We have 3 elements, right? What's 2 to the 3rd?
8.
It's 8. So however many elements there are, the number of subsets is 2 raised to that power. I did this example with 3 elements on purpose. Because pause for a moment and consider, what if I just had, say, 5 elements? What's 2 to the power 5? Anybody know?
5.
Nope, that's 5 to the power 2, so you flipped it. Try again. Bigger than 16? 32. You got it. It's 32. I do not want to write out 32 subsets, do you? Nope. I don't really want to write down 16 subsets or 25 subsets either, right? So it becomes really big really quickly if you're just trying to figure it out by listing them all out. So it's very nice that we have a concise formula that tells us it's 2 to the power of n. Now, if you're looking at this group, most of these are proper subsets. Remember, proper subsets means they're a subset and they're smaller than the whole thing. So if I'm looking for proper subsets, that one counts and that one counts and that one counts and all 3 of these do, and the empty set does as well. How many of these are proper subsets? There's 7 of them, right? So what do? Well, I just take the 2 to the n and I take 1 away. Okay, so if I had the 2 to the 5 and I had the 32 and I took 1 away, I'd have 31 proper subsets. Does that make sense? So I probably have spoiled the fun because I did look at number 6. How many elements are in 6?
5.
There's 5. I should have used a different example. That's okay. The number of items in this set. How many items are in set A? 5. All right, so this problem says it wants us to find the number of subsets and the number of proper subsets. So the number of subsets is always 2 to the number, the power, is going to be the number of items in the set. 2 to the 5th, we did this out loud just a minute ago, it's 32. And part B is always taking that 32, or whatever that value was from part A, and taking 1 away, and I get 31. So there are 32 subsets, and there are 31 proper subsets. This is a really good example of places where if you're doing a quiz or an exam, what happens on quizzes and exams is once the period that it's open for closes, I go in and I edit your answers. I don't edit your answers. I edit the credit you're getting for your answers. So what will happen is, let's say you screwed up part A on this and you accidentally counted that wrong. Maybe it was more than 5, right? So you counted it wrong and you thought there were 6. Well, if you counted 6, you're going to mess up part A, right? You're going to get part A wrong. But if you know that you're supposed to subtract 1 for part B, that's actually information that you know that you shouldn't be penalized for just because you messed up part A. Does that make sense? So this is a really good example of one where I go back in and I check to make sure. I do it on all the problems, but this is a place where it will often happen where somebody makes a mistake on A and I can still give you half credit for the problem on B because you did part B right. I don't go back in for your homework because you have multiple attempts at your homework, but I go back in for quizzes and exams. Okay? So it's always one fewer on part B. All right, number 7 lists it differently. It actually gives that set notation. It says x, such that x is an odd integer between -9 and 4. And it probably would be a good idea for us to simply write out what those values are. So what are our odd integers between -9 and 4? Well, let's first start out with -9. Do I get to include or not include -9? I do not. Between means it doesn't include. So I do not include -9. So what's the first odd integer after -9?
-7.
Yep, -7. And then?
-5. -3.
And then that's all. Good. Okay. So this is another description. It's the listing description, right, or the listing method for all of the elements in B. So what are the number of elements now then in B? There are 6. So part A, I need to do 2 to the power of 6, which is at 64. And you guys have calculators, just grab them if you want to, right? And then we take 64 for proper subsets, take away 1, and we have 63. Okay, any questions on those? All right.